An absolute value equation is one like this. The absolute value of x is equal to 5, where on one side we have the absolute value, and on the other we have a number. It's very easy to solve this one because you can guess the solutions. There are two. I know that the absolute value of positive 5 is equal to 5, and also the absolute value of negative 5 is 5. This means I have two values that make the original equation true. So a good strategy for solving an equation like this is you copy down what is inside the absolute value, which is simply x, and then you would set it equal to 5 on the other side. But you can also set it equal to negative that number as well, and it gives us both of the solutions just because it was a very simple expression. The second part of this is since we have a graphing calculator or Desmos, we can look at the solutions on a graph. So I have graphed over here two equations. Y is equal to 5, that's the right side, and the absolute value of x, which is the left side. And any solution is where the two graphs meet. So I have a spot here and a spot here. And they line up perfectly at the two numbers I expected, negative 5 and positive 5. So here's like a really simple way to, if you want to check to see that your answers are true, what you can do is say, okay, in place of y1, I'll place one side. In this case, I chose 5. For the other side, for y2, I put in the absolute value of x. And then you can go to your table and see if the numbers do in fact work. So like I said for this one, it's simple enough to just take the x, let it equal in this case 5 and negative 5, and we get our solutions. But you can then also check to see that your answers are true by looking at your graph. For example 1, it's a very similar question. It's still an absolute value is equal to, in this case, 5. It's just that the expression inside the absolute value is more complicated. If I want to solve this, I'm going to use the same strategy that we did in the previous part of this lesson. Basically, you take the piece inside the absolute value and you set it equal to 5. But if you also set it equal to negative 5, these are two separate equations, both of which make the original statement true. What this is saying is you're taking 2x plus 1, and if you set it equal to 5, you're saying put 5 in place of this portion, and you would get the absolute value of 5 is 5. This second equation is saying take 2x plus 1, but make it equal negative 5. It turns out that that number works in the equation as well. So for absolute values, there are two equations to check. They're both very similar and very easy to solve in this case. For 2x plus 1 is equal to 5, I'll take 1 from both sides. I get 2x is equal to 4. Then if I divide both sides by 2, I get x is equal to 2. My other equation, it's very similar, so the process will look pretty similar too. I'll still take negative 1 from both sides. I now get 2x is equal to negative 6. And if I divide both sides by 2, I get x is equal to negative 3. So I have two solutions, 2 and negative 3. So the second part of this process would be, okay, can I check this on, let's say, my graphing calculator? The way I would do that is I'll put y1 equal to 5, and that would give me this portion here. That is the right side of the equation. And then for y2, I'll place in the absolute value of 2x plus 1. And this is the picture that showed up on my screen. And I can see that there are two solutions. There's two places where these graphs are equal. There's a spot here, and there's a spot here. All I have to verify is, do the x values match up with the two values I have here? If you look at the graph, okay, we have this spot, and that is negative 3, which is great. I mean, that corresponds to this solution here. My other location is positive 2, and that makes sense as well. That corresponds to this solution here. So again, the great thing is, if you're starting with this absolute value equation, it's pretty easy to solve. But if you want to check your work, you can graph one side, graph the other, and see if the place where they meet is equal to the values that you solve for. And for example 2, same question, but now I'm just looking at an even more complicated absolute value equation. So this time, I still have the absolute value of 2x plus 1, but I'm not setting it equal to a number. I'm setting it equal to another absolute value equation. And then over here, I just graphed both of these. And this time, there are two separate absolute value equations. If I want to first solve this without using a graph, I have to set up two equations. And it will look very similar to the previous examples. Here's the first one. You can say 2x plus 1 is equal to 4x minus 7. What this is saying is, if the two things inside the absolute value are equal, if you then take the absolute value, equality still holds. Let's solve this. Okay, to solve for x, I think what I'm going to do is I'm going to add 7 to both sides. I get 2x plus 8 is equal to 4x. I'll then subtract 2x from both sides. And I get 8 is equal to 2x. And after I divide both sides by 2, I get x is equal to 4. But with absolute value, there's potential for a second solution. So we're going to set up a second equation. My other equation will be, all right, I'm going to write 2x plus 1. And what we did in the previous examples were just make the other side negative. That will hold here as well. I'm just going to be careful with how I write it. I'm going to make 4x minus 7 negative 4x minus 7. What this equation is saying is, leave one side alone, but if the other side were the negative, after you apply the absolute value, it would become positive again, so equality still holds true. These are the only two equations we have to check, where they're the same or where they differ by a negative. So in this new equation, I think it's going to give us a second solution. So to solve this, I guess I'll first distribute the negative into the parentheses. So I have, on the left, 2x plus 1. That didn't change. But on the right, I have negative 4x plus 7. Okay, I think I'm going to add 4x to both sides. And when I do that, I get 6x plus 1 is equal to 7. And if I subtract 1 from both sides, I get 6x is equal to 6. I think this is going to work out great, where after I divide both sides by 6, I do get a second number, a different one. X is equal to 1. I have 4, and I have 1. If you now want to check your work, you can plug both of these equations into, let's say, your graphing calculator, or like I did over here, this was from Desmos. The way I set this up is, this graph here was the absolute value of 2x plus 1. That makes sense because it has a y-intercept of 1. So I'll say for one of my graphs, I put the absolute value of 2x plus 1. That was the red one in this case. And my other equation for y2, it's not a horizontal line. It's actually a second absolute value equation. So this was 4x minus 7 in absolute value. And that matches up too. If I look at this blue equation, it has a intercept of 7, which agrees with, well, in absolute value, it would become positive 7. So the two equations do in fact match up. Now let's check our solutions. The graphs meet here and here. If I compare that to the corresponding x values, for this point, I look down to the x-axis and I get 1. If I check my second point and I look down to the x-axis, I get 4. And that's perfect. If I look at the two numbers that I solved for here and here, I got 1, I got 4. I can see from my graph that there's nothing else that could possibly work. So I'm convinced that, okay, I have all this work here and it gave me my two numbers. I verified it on my graph, and that is it for this example.